Welcome to Brain Vision.
Hello everyone, this is the solution to problem 44, chapter 24 of Cosmos Physics. And we're asked to find the intensity coming out on the other side of a polarizer that is rotated through an angle alpha, which varies between two parts of the problem with respect to the vertical. So let's go ahead and take a look at the first part. Here in part A, we have an unpolarized light incident on this polarizer. And so the intensity that's coming out on the other side, so S on the other side, is going to be equal to half S incident, which is just going to be 3.5 watts per meter squared. Now this is because we started with unpolarized light, and so as we polarized it, we lost half of its intensity. On the second part, the transmitted one, so on part B, we have a polarized light coming in from the left that is polarized in the direction of or along the axis of the Polaroid, and so the outcoming intensity is going to be exactly the same as the incoming intensity. So this is just 7.0 watts per meters squared. And in part C, we have light that is polarized in the y, along parallel to the y-axis, coming onto a Polaroid whose polarization axis is parallel to the z-axis. Now these make 90 degrees with each other, and so the outcoming intensity is going to be 0 watts per meter squared. So these are the answers for the first part, for the rotation angle being 0 degrees. Now what happens when we rotate through 35 degrees? So we have these situations that I've sketched out here. So here, the answer to the first part A, is again that the outcoming intensity is going to be half times the ingoing intensity, which is again just 3.5 watts per meter squared. And the reason for this is quite obvious, because you had unpolarized light coming in and you polarized it again in some random direction. But when you do this, you always lose half of the intensity of the electromagnetic wave. Now, for the second part, we have a polarization along parallel to the vertical direction, parallel to the z-axis. And so since this polarization axis of the Polaroid makes an angle of alpha between the vertical, it's the same as saying that the polarization of the electromagnetic wave makes an angle alpha with the polarization axis of the Polaroid. And so we have that S bar is going to be S0 times cosine squared of alpha. And working this out, this gives us 4.7 watts per meters squared. What about the last one? Okay, so here, for the last problem, we have a wave coming in that is polarized parallel to the y-axis. Now the y-axis makes 90 degrees with the z-axis, but what we have to figure out is what is the angle that it makes with the polarization axis. So if I have that, I have alpha over here, and this is the y-axis, this is the z-axis. Then obviously the y and the z-axis make 90 degrees with each other. And if I rotate or have a random direction that is lying between these two axes, that is rotated through an angle alpha, then the angle over here is going to be 90 degrees minus alpha. And so the light coming out of this is going to be S0 times cosine squared of 90 degrees minus alpha. And well, alpha is 35 degrees, so this is going to be 55 degrees and we end up with 2.3 watts per meter squared. So these are our answers to the second part. And just to clarify what's happening here in the last part is the reason that I'm using cosine squared as opposed to sine squared is because I found what the axis of the polarized light makes with the axis of the polarization, and so I can rotate towards the angle. I can rotate through that angle that I had found towards the polarization axis. So anytime you have a situation where you have some random direction enclosed with another direction that is perpendicular to the first direction, you always use cosine when you want to project this line over here, say, onto this axis. If you wanted to project this line onto this axis, you would use sine alpha. But you project onto this axis, you project through the angle, you use cosine.